No time lapse.
Electroscope. Okay. All right. Good morning, ladies and gentlemen. 2016 practice test. Start off by doing multiple choice numbers 11 and 19. If you have questions, ask me in class. Now's the time.
Yeah.
Okay. So review for you. You should have this in your notes already. See if you can find it. Okay.
This is stuff about the atom parts.
Yeah. We got protons, neutrons, electrons. Symbols for each. Protons positive. Electrons are negative. And can they be removed? Neither of these can be removed, but electrons can be removed.
Yep.
Normal atoms are neutral and have the same numbers of protons and electrons.
You guys know this already. This is review.
The basic unit of charge is 1.6 times 10 to the negative 19 coulombs. And charge is quantized in integer multiples of that number.
Yep. So you've got one electron. The charge on that one electron is negative 1.6 times 10 to the negative 19. If you have two electrons, it's 3.2 times 10 to the negative 19.
Multiply it by 2.
That's right.
And if you got 3 of them, multiply that by 3.
Sorry about the light show going on here with the
Oh
projector.
no, is it doing it?
Yeah, it's the projector.
Dang it. Okay. We just did this one. Okay, a conductor allows electrons to move around freely. Metals are conductors.
Yeah, remember the electroscope? It's got a metal knob and electrons. It's a conductor, can run anywhere in the electroscope.
When electrons are placed on a conductor, they move around to get as far away from each other as possible.
You can demonstrate
Let's
that
see,
if you
should we do
want.
this now?
Yeah.
Okay. So right now these are both neutral, if you will. And I'm going to go ahead and rub this. Wait, what should I use?
Doesn't matter.
Okay, well, here we go. I'm rubbing this. I'm rubbing electrons from here onto here.
Yep.
Negatively charged, positively charged. Now, I'm going to go ahead and rub this on here.
She's rubbing electrons off of the rod onto the electroscope, and they're running away from each other to get as far apart as possible. And here that they can exert a force on each other.
Yeah, and why is that? Because this is a conductor, and they want to get far away from each other as possible. So, did I just click that by accident?
Yep.
I did. Okay, so...
Well, insulators don't let electrons move. That's
What's that? It's missing it. It's missing the slide. Okay, an insulator does not let electrons move around. And there's another insulator right here. That little rubber thing right there.
Yep.
Okay, which means that electrons just can't escape through there, which is a good thing.
Yep.
Okay, for our lab. Grounding. Electrons move into or out of a large reservoir of charge. The Earth, me, you.
Why don't you ground this thing right here?
And ba-da-doom.
Boom. So she gave the place for the electrons to escape. They went into her.
There we go. They went into me and then ultimately back into the
That's grounding.
Okay, that's grounding. Coulomb's law. You guys are familiar with this. This is the generalized Coulomb's law. We've got the electrical force. We've got our constant K. We've got the charge 1 and charge 2, and the distance between them squared.
Yep.
Now, when we are speaking about an originating charge and a test charge inside that field, now is when we get more specific with our variables.
Yeah. If you want to measure the existence of an electric field in space, then you have an originating charge that's producing the field, and then you have a test charge, which is that
Used to measure
little
it,
red
right?
thing over there.
Okay, this all being.
Yeah, and so it's just an
It's the same thing.
application of Coulomb's law for
Yeah.
a specialized situation.
Okay, work done moving a charge in an electric field is stored as electrical potential energy. Okay, so if I throw in this positively charged test charge, it is going to...
I've got it upside
I was gonna
down.
say, you got that upside down, right, Mr. Wayne? Okay.
So if you take an electron off the top, it makes the top negative. If you put the electrons on the bottom, excuse me,
Should I go through that step by step with them? And pump the electrons?
no, you did, well, you have a positive test charge. You did the same thing I did. Take an electron off the top, makes it, just put plus signs on the top.
Yeah, okay, so these are
Take
plus
an
signs.
electron off the top, it becomes positive, a little bit, bottom comes negative, positive, negative, positive, negative. And then draw the electric field on the inside.
Yeah.
I forgot to do that. And the direction of the electric field is out of the positive, into the negative. Out of the positive, into the negative.
What's this called again, Mr. Boykin?
That's the electric field.
Just like the whole
Oh,
thing.
capacitor.
Capacitor, right? and this is our electric field, right?
Yep.
And sorry for butchering that earlier, you guys, but essentially what we're doing with a capacitor is we're taking, it's neutral to begin with, right?
Yep.
And we take an electron here and we put it over here, making this negative. Henceforth, I haven't used that word all year, making that positive.
So,
Same thing.
and now we've got our statement here. Work done moving a charge in an electric field is stored as electrical potential energy. So you go ahead.
This is our positive test charge now, and when I throw it in here, what's it gonna do?
Repel from the positive, attract to the negative.
Right? And so now if I do work moving it against the electric field,
Okay. That's stored as electrical potential energy because you had to do work to get it over there. And what happens if you let go? Falls
okay,
back.
well, it falls back right here. Okay, and it's just like but it's not.
Electrical potential energy.
Yeah, electrical potential energy. Okay, and we see it right here. So this is our string of equations that we can use. Electrical potential difference is right here. This is our electrical potential energy.
So you do work moving a charge from one side to the other. You apply a force through a distance that changes the electrical potential energy. But how much work you do depends on how much charge you've got. If you have a larger charge, takes more work. There's a constant relationship there.
Yeah, there's a ratio there. Okay.
And so the amount of work you do divided by the quantity of charge you moved is the electrical potential difference. That's the difference from one side to the other. The difference in electrical potential energy down here. It's got electrical potential energy down here. It's got it up here. What's the difference between the two?
It really just reminds me of UGG, you know.
And you measure that with a voltmeter.
Same ideas. Yes, voltmeter. Thank you for adding that. And then what's our unit for volt? For volt? I mean, we got for our electrical potential difference, it is volts, right?
Joule per coulomb.
And joule per coulomb totally makes sense because joules per coulomb.
Yep.
Right? Okay, last but not least, go ahead and also do numbers 18 and number 20 from the practice test. And the practice test is at the very bottom of this module.
Yeah.
Just go ahead and click on it, scroll through it, find your questions.
And that's it.